So let's get started. First of all, my name is Stuart Welsh, as you know. You can find me on Twitter at Maths180. And if you're interested in any of the work I've done, then you can have a look at my website, maths180.com. As Mark McCourt said in the introduction, today's hashtag is hashtag MathsConf23. So if you're on Twitter and you have anything to say, then it would be fantastic if you could share that with us today. So first of all, just a quick bit of geography. Obviously, the conference was supposed to take place in Oxford, and many of you, I'm sure, are in the UK, but of course, I know that there are people joining us from all over the world today. Some folks in as far away as South America, very early in the morning for them, and some folks, I think, in Australia, obviously later into the evening now for them, so perhaps staying up with a few beers and enjoying the conference. So wherever you are in the world, welcome to this presentation. I myself, I'm actually at the moment in Andalusia in Spain, down there very close to Gibraltar. And obviously you saw Mark McCourt giving us our introduction. You may have heard the birds twittering in the background. And no doubt Mark is at his luxury villa, which is very close to me. I'm not sure why Google auto-generated that little icon for Mark's luxury villa, but it seems quite fitting to me. Anyway, time to get on to the business of today. Throughout this PowerPoint, or throughout this presentation, I've used a very sophisticated color coding mechanism. Red, essentially, is some of the reasons why I feel maths learning is hard, why students find it difficult. And anything you see in green, those are the good things, those are the things that we can try to do to help students. So I've split this presentation into three sections. Initially, the first part here, we're going to look at some theory, some of the theories around learning in general and learning maths specifically. Then we'll move on to a section which I've kind of called Why Students Make Things Harder for Themselves and what we can maybe do to help them there. And then finally, the third section will be why we might be making maths learning harder for students and what we might be able to do differently. So as I said, I'll start with some theory. And in his work in the 90s, David Geary tells us that all knowledge can be classified into either biologically primary or biologically secondary. And I might just take this chance to show you that at the bottom of this page, and you'll get these slides later on, they're also available on my website, so you don't need to take copious notes, that at the bottom of every page, where possible, I've included a hyperlink to research papers or websites or anywhere that I've gathered the resources. So as I say, the website, my website will have these slides, so you can use them. And I've actually included quite detailed presenters' notes, so when you do get hold of these slides, if you're interested in them, a lot of the information I'm telling you today will be included in the notes. So carrying on with Geary's work here, biologically primary knowledge, which some of you may know, is knowledge which Geary claims we've evolved to acquire over many generations, often for reasons of survival. So biologically primary knowledge, it doesn't usually need to be taught, and it tends to be acquired with relative ease and speed. So some examples of biologically primary knowledge would be maybe learning to speak, learning to read faces, learning basic social interactions, and general cognitive skills such as basic problem solving and self-regulation. Biologically secondary knowledge, in contrast, is knowledge that we've developed for cultural reasons, and it tends to be acquired relatively slowly and requires conscious effort. Biologically secondary knowledge has emerged relatively recently in human existence, and since we haven't evolved to acquire this type of knowledge easily, then explicit instruction is required for us to learn it. And so examples of biologically secondary knowledge include learning to read and learning to write. So a good example here is if you think about how quickly and easily, relatively, a young child or baby would learn to speak. However, we want to think then how difficult it is for that same child to then learn to read and write. So you can maybe see the contrast here he's trying to make. So it turns out really, which is not great news for us, that pretty much everything that's taught in schools can be considered biologically secondary knowledge. So that means that school learning is hard, full stop. It requires effort on the part of the learner, and the success is dependent on the quality of instruction and the quality of learning experiences on offer. So speaking of effort, as teachers, we could study every theory of learning that there is. We could take part in every MathsConf, and we could design and use the best learning tasks. But if students aren't willing to try hard, then they're just not going to make as much progress as they might. So there's lots and lots that we can do on our side, but students have to play their part too. And I think it's important to remember that. Now, in his absolutely fantastic book, Memorable Teaching by Peps McRae, he describes attention as being the currency of our classrooms. And giving attention is a choice, and it requires effort on the part of the student. So no matter how we try, we can't really force them to pay attention. However, if they do make that choice and give their attention, then what we can do is we can try and influence what they attend to. So you might be familiar with John Sweller's work on cognitive load theory, and it is much more than just the simple idea that giving students too much at one time is not good for them. The work that you can see linked to on this slide has been done in New South Wales, and it shows how cognitive load theory has grown into a complete model for schooling, and that link definitely worth following and definitely worth reading. So in my very basic summary of cognitive load, basically consider working memory limitations, present new material in small steps, and eliminate the unnecessary seductive detail. And I've been doing my best with this presentation here to keep it streamlined and simple, and perhaps a little bit minimal, but trying to follow those principles of cognitive load theory. So Richard Skemp, way back in the 60s, basically summed up what our job is. Told us we should focus on these three deceptively simple looking points, and the link there on the slide will take you to Skemp's paper, which is definitely worth reading. We need to consider how learning works in general, look at what are the most effective teaching methods, and then we want to think about how we would apply that to teaching maths. And I feel these 3 points here, which are influenced by so many people in the maths field, I feel this is a good summary of what we should hope to see emerging as students travel along their mathematical journey. So if new learning builds on existing knowledge, and if we accept that learning is a progressive change in what a student knows and what they can do, then without a solid and reliable knowledge base, students will struggle to make sense of any new learning. And I feel this is especially true in mathematics, where there's so much content and so much of it relies on what has come before. Again, this is a quote from Richard Skemp, and given that the ideas in maths link up in such a richly interconnected and hierarchical way, then learning maths is going to be very, very hard for students if they just don't have the knowledge of the facts and the procedures to draw upon. So considering that hierarchical structure, this is my best attempt at trying to look at some of the prerequisites that go in towards just a single, quite simple, I suppose, concept within learning maths, the idea of adding fractions. And although you could probably think of more, these are the basic sort of prerequisites that I can see feeding into adding fractions. And then, of course, if you think about those that second layer there, that outer ring almost of prerequisites, then they also have their own prerequisites that feed into them. And we could continue to expand this web out the way. And so it is a complicated process trying to build that hierarchical schema of knowledge, and something we really should be making sure we pay consideration to. So we must think about this when we're sequencing our courses, but also it's so important to test that prerequisite knowledge. You could use questioning and quizzing, and if it's not there, then we need to teach that. The prerequisite knowledge has to be there. It's never wise to assume that students know something just because it was in last year's course. I suppose my advice is don't start something new until we are sure that they know everything that's required for that new topic. Now, learning maths is extra hard because much of it exists in the abstract. Obviously, we can count 7 objects. We can count 7 objects. We can't count X objects. We can see and we can feel what it means to add on 3. But what about subtracting -3? That world of abstraction is something that we really need to consider when we're thinking about how best to teach mathematics. And then we move into this idea of conceptual understanding. And forming conceptual understanding is very different to learning facts. Now, there are facts that students need to learn and remember as we go through mathematics, but this deeper idea of conceptual understanding underpins successful progress in maths. New concepts are formed by combining or modifying lower order concepts. So that means that conceptual development is essential for successful learning in maths. However, Richard Skemp suggests we can't teach concepts. We can only provide situations for students to form them for themselves. So the individual steps or moves of, say, solving an equation usually involve some or all of the 4 operations. Maybe we do something with brackets and then done. However, the actual act of solving an equation is much greater than the sum of these constituent parts, because we've done something more than just subtraction and division. We've actually solved this equation. And if this is formed as a concept, then students can apply the same concept to similar problems involving different moves. And then they can make the connection from this concept to other related concepts, like, for example, rearranging formulae. Now, I'm sure you've experienced this. The process of dividing a value, or the process of dividing by a value between 0 and 1 is, on the surface, a pretty mechanical procedure. The fact that the result is larger than the original amount quite often surprises students, and explaining the why behind this takes time and usually several examples until the student sees for themselves what is happening. But quite often you do get that aha moment with them, and once they've formed this concept, they can connect it up with other concepts like multiplying by values between 0 and 1 and so on. So this aha moment is something students need time and space to experience for themselves, and it's actually central to the Gestalt theory of learning. And for me, anyway, it feels like a good description of concept formation. Now, I just made up 6 questions here, but essentially this could be a question from any school mathematics textbook. I'm sure we've all seen something like this. And what we want to think about is whether there is really any learning in this task. For me, you'll either get the answer right or wrong here. But if you get it wrong, is there any real way of improving what you know other than then just looking at the correct answer? So although we can't directly control what students think, through task design, perhaps we can try and influence what they think about. So instead of this example, trying to test knowledge of place value, how about this instead? And you can see here that this task, where it might be a little bit more complicated just in explanation, then what we're doing here is testing knowledge of place value. And if the student is successful and manages to perform the correct subtraction, so in this case the first thing would be subtract 100 and then subtract 20, etc., then they'll start to see that they're turning all the digits to zeros. But if they're wrong and they subtract maybe 10 at the beginning instead of 100, then they'll see that the change that's happened was not the one they expected, and they can go back and revise and try a different approach. So with this task here, this simple little shift hopefully creates a task that allows them to self-correct and to try and make a little bit more sense about what they're learning. And that task in particular, you can see there, comes from the wonderful ATM book, the Practicing Mathematics, which you can link to from the bottom of this slide. Now, I saw one or two questions in the chat there just about the slides being available at the end of the presentation, and I believe that LaSalle and Complete Maths will be making the presentation available, and this presentation will also be on my website, which is maths180.com, and on that website you can find all the presentations that I've done over the years and some journal articles and just all sorts of resources and stuff, features, and which you can download and use for free if you want to, plus hundreds of video lessons on all sorts of topics of mathematics. So it would be great if you wanted to check that out. So here's another kind of standard, I suppose, looking task, just in testing order of operations here, which is absolutely fine, and obviously we want pupils to be able to deal with this. But again, maybe we can think, can we get a little bit more from this task? Can we make this a little richer in some way? And so then perhaps we can with something along these lines. Now, this is a task from Chris McGrain's website, which is a wonderful, wonderful site. The link is at the bottom of the slide there, startingpointsmaths.com. So many great tasks there, which just take the normal exercises and open them up into something where maybe a richer learning experience can be had. So that's the end of part one, and now we're moving on to this second section here, why students might be making maths harder for themselves and what we can maybe do to help them. And much of this will be common sense. I think, I hope most of what I say today sounds like common sense, and if it is nothing more than just a reminder of some of these things that are important, then I feel that this presentation is doing its job. One of the things that students do that makes their life harder is the sad fact, whether we like it or not, that some of them just believe that maths is hard. Parents and brothers and sisters, siblings, even teachers sometimes tell them that maths is hard. They get this idea that you're either a maths person or you aren't. And students are then able to attribute their lack of success to this. Plus, students are prone to saying things like, the test was too hard, or we haven't been taught it. If you look at some of Bernard Weiner's work in the mid-80s, he tells us that the perceived cause of academic performance is as significant as the actual cause. So basically, the reason why you think you haven't done well is as significant as the actual reason that you didn't do so well. And if this perceived cause is something stable, like maths is hard, or I am not a maths person, then what happens is students will just continue to expect the same results in the future. There's no way out for them. So our job here is to try and shift students' thinking away from factors that they have no control of and onto factors that they can control. For example, more effective revision, identifying and working on their weaker areas, and so on. Continual positive praise doesn't work because it loses its worth and its value over time. And I'm afraid motivational posters and one-off assemblies don't work either. Instead, what we need to do is look for opportunities to create micro moments with students. And by that, I mean just taking an extra few seconds to give some praise about the way they've overcome a difficulty. Highlight the action that they've taken and show that you value it. So maybe an example of that would be, instead of saying, well done, that was a difficult question, but you got it. Just take that extra second to say something along the lines of, I could see you struggled, but you looked back at some earlier examples and that helped you make sense of it. That's what helped you solve it. Well done. And just that subtle shift to what they did to have success is enough to just start changing that thinking towards the fact that they can make a change to their success. And if we do that frequently enough, then the laws of marginal gains should hopefully do the rest for us. So related to attribution theory is self-efficacy and anxiety, and Alfred Bandura, way back in the 70s, did some fantastic work, and you can see his paper there is linked on the slide. And he defines self-efficacy as one's belief in one's ability to succeed in a task or to accomplish a goal. And students with low self-efficacy will shy away from challenge and view new material as a threat rather than an opportunity to learn something new. And self-efficacy, though, can be boosted by having success or even by mastering a topic. And we want our students to know that we value learning instead of knowing. And we should focus our feedback on personal progress rather than focusing on mistakes or making comparisons with other students. Whilst it's believed that intelligence is heritable, knowledge is something that can be acquired, and struggling with maths now does not mean that you will always struggle. We should give students a chance for success by determining their level and giving them work that is challenging, but that they can succeed in. Siegfried Engelmans tells us that students need to be appropriately placed in the instructional sequence. And he goes on to say that the appropriate place is not at the edge of knowledge. The appropriate place is actually where students will make some mistakes, but not too many. And this idea is supported by Barak Rosenshine's Principles of Effective Instruction, which are also linked on the slide there. His advice there that we should be aiming for that high success rate. So with this success, self-efficacy increases and students will be more willing to take on harder work. Success leads to motivation, which leads to further success, that upward spiral. So many students demonstrate a performance goal orientation. That means that these students are motivated by a desire to prove their abilities, and a culture of high stakes assessment, competition and grades just fuels that orientation. However, students with a performance goal orientation tend to fear failure, and they will choose easier tasks rather than risk being wrong or looking bad. And sadly, again, often well-meaning parents don't help and can sometimes perpetuate this performance orientation. And our job then is to shift students towards a mastery orientation. Students with a mastery orientation are motivated by the opportunity to develop and master new skills. It really isn't easy to do, but we do need to give students the message, like I said before, that we value thinking over task completion. We value personal progress over performance, and using frequent no stakes or low stakes assessments can help here, as would reducing grading and ipsative assessment, which I know Andrew Woods is going to talk about in session 2. That has the potential to help us here, where students are held more accountable for responding to feedback and demonstrating progress relative to their own work and not to predetermined standards. So I hope some of you are joining Andrew's session 2, but if not, I do believe that all sessions are being recorded today and should be made available later on. So if you're not sure of ipsative assessment, then it's definitely something that's very interesting and worth looking at. Many students see maths as a series of unrelated procedures that they need to memorise, and sometimes, I'm afraid, that's because it's taught that way. For some students, it's the only strategy that they have when it comes to learning maths. But some students do remarkably well with this approach, and I've no doubt that some top set students are in that class because they've become very good at the game of remembering what the teacher said and then applying it at the right time. And they can go very far with school maths, all the way through school maths successfully, especially when a lot of exams are largely predictable and actually cater quite nicely for this memorising approach. Now, don't get me wrong, they do need to remember all of it. Students need to remember all of this stuff, but if you have a course plan that essentially looks like this, what sometimes might be called a conveyor belt curriculum, then you can see from Ebbinghouse's work on memory there that end of topic tests, they'll do fine, they've remembered it, but they will forget it over time. So we need to make sure that by the end of the year, we haven't just forgotten everything that we've covered. And teachers have been doing this for decades. Review homework exercises, mixed homework exercises, trying to keep those plates spinning. But there is a lot we can do to help students with memory. And one of the big things we can do is try and help them see the connections that exist across topics and across concepts, because if we can help them conceptualize the bigger ideas, then they can start to transfer those concepts across to other problems, and also link those concepts with other concepts to create a really rich schema and a deep understanding, which doesn't rely on remembering lots of granular parts. Rather, it just keeps a memory of big ideas. Now, if you search online for how do I get better at problem solving in maths, it's like half the internet is dedicated to answering that question. It is a real struggle that students have, and often they don't know where to start when it comes to solving a problem. They're uncomfortable when they're not able to see the solution path immediately, and they'll rush in with poorly formed strategies, and quite often ignoring or missing completely the structures and the relations and the meanings that lie there beneath the surface. So knowing where to start with a problem is probably just about as important as knowing how to solve it. And throwing students in at the deep end, so to speak, with a problem, it's probably not the most effective way of helping them, as they tend to search the problem space, which is their internal conceptualization of a problem, randomly rather than selectively, just flailing about, essentially, hoping to catch hold of something. Now, this might lead to a solution, but it isn't really an efficient or a reliable approach. We want to have students to have enough existing knowledge so that they will work in a more systematic way, and having mental models of similar problems will help students with problem solving. I sometimes use the analogy of an Olympic bobsleigh driver at the top of the run, just about to go down the bobsleigh track, and the night before, that driver has spent hours mentally rehearsing every single turn, twist, breaking point, etc. on that track. They have that mental image secure and ready, so that when the beeps go and they start heading down the bobsleigh, then they can rely on that solidly formed mental image to steer them safely down the track. Now, I'm not suggesting that we do any Olympic standard bobsleigh work, but the teacher is definitely the best person to be modelling this problem solving. We should model problem solving with students as if we are also novices, and thinking aloud about our decisions, our reasoning, and our choice of strategy will help. If we limit problem solving to just simplistic examples, then what we're doing is limiting the options of students when they have to solve problems by themselves. Having students solve problems might lead to solutions, i.e. the problem's goal state, but it doesn't necessarily teach students how to solve problems, which is education's goal state. So that's us now on to section 3 of our presentation. And so I'm just checking the chat window to make sure that people are still with us, which is great. It's very sort of strange being here just in my room on my own in the silence, but it does seem that people are still. Thanks, David. Brilliant. Apologies if I haven't answered any questions. We may well have some time at the end for questions, and if so, then hopefully we can deal with those. So let's see. I don't know if this is comfortable reading or not, but it could be that we might be making learning maths harder for students than it needs to be. And here are some of my thoughts on how we might be able to do things slightly differently. So cognitive scientists and educational psychologists have been working really hard for decades trying to figure out how learning works and how we can maximize it. The problem is that that research has just not been getting to the classroom. And so teachers have been relying on what I call folk teaching, and doing the same thing that we've always done because it kind of works. And reality is that it does kind of work. We have been successfully educating students in mathematics for a long time now. So we're not talking about wholesale change. We're at this point where we're now trying to make those marginal gains, those little shifts that can take us to the next stage and just incrementally improve pupils. So over the past few years, and I'm sure many of you are familiar with and have perhaps even attended conferences and events like Research Ed, for example, this knowledge from the laboratory and also in the field is finally getting to teachers in a form that they can use and that they can understand. And this is a big area that I'm really very interested in. And although we don't have time today to go into it, because I could probably take over the entire MathsConf talking about the science of learning. I did write an article in the Scottish Maths Journal, which you're more than welcome to obviously have a little look at, and any feedback you can send to me on Twitter, but the link to it is there. All sorts of great stuff, Scottish Maths Journal. And in there we talk a little bit about acknowledging cognitive theory, thinking about the demands of working memory, but also things like practice testing, capitalizing on the effect that actually more assessment is good so long as it's low stakes, the retrieval effect, spaced practice, interleaving, all of these wonderful things that have emerged from the science of learning, which are backed up by evidence, which works not just in the laboratory, but also in the field, and not just in the case of memorizing random syllables, which is what Ebbinghaus did in his famous work, but actually also with mathematical procedures and problems. So there's a lot of great research there, and if you're interested in more of it, then, as I say, I mentioned it in that article, but I don't want to talk about that too much more just now. I do want to move on to this idea here of Dave Hewitt's. He talks about viewing the maths curriculum in its content in terms of arbitrary and necessary. So there's a link there to Dave Hewitt's article. There's actually 3 parts to this, but part 1 certainly gives a good overview. Hewitt tells us that arbitrary content cannot be worked out. So the best way to explain what I mean by that is probably through some examples. Examples of arbitrary content would be the names of shapes, for example, squares, rhombus, etc. Now, there are possibly some reasons why we've chosen triangle to do with language, but really it's just random. We could have called them anything. It doesn't really matter. That might have been something else. A square doesn't have to be called a square. Also, things like the symbols that we use for addition and subtraction. Again, there may be some little ideas, but it's something that we can work out. It's not a necessary result of maths. 360 degrees in a full turn. I mean, that's a classic. There is obviously some historical reasons why that came about, but really, again, that's quite a random, arbitrary value to put on there. And even words like hypotenuse, conventions that we use like function notation, those things we've just decided upon. So students need to be told this arbitrary content. They're not going to figure these things out for themselves. And if we don't tell them, then there's a danger they might make something up. Arbitrary content exists in memory. And Hewitt suggests that if students are working with memory alone, then they're not actually doing mathematics. So necessary content, on the other hand, it can be worked out, it can be deduced. And Hewitt says that this content exists in the realm of awareness. And I'm going to keep using this word awareness. So examples include the angle sum in a triangle, the concept of primeness, common denominators, why we use them for adding fractions, inverse operations for solving equations. These are all necessary results that can be deduced or can be, I don't want to say discovered, but it can be achieved or got to through careful explanation. Also, dividing by a fraction is the same as multiplying by its reciprocal. Students can see these things for themselves. Some of them will have the awareness to work it out for themselves, of course. And Hewitt says, and I definitely agree with this, that our job is to create opportunities for students to use their awareness to come to see what is necessary. If we tell students something which is necessary, that is treating it as if it was arbitrary, then it just becomes something to be memorized. And Hewitt calls this received wisdom. Now, some students will have the awareness to make sense of it anyway, and in that case, they will turn it into a necessary result. However, many will not. And too often, students don't make sense of the why, and this just becomes another fact to remember or perhaps to forget. Some examples of necessary content that I think may be sometimes taught as arbitrary includes triangles in a circle have a right angle, or angles in a triangle sum to 180 degrees. The 4 operations with negatives, 4 operations with fractions, stuff that there's a lot of deep thinking involved in explaining why we do what we do, but I think many students may just find that that's given to them as received wisdom. So those are just some examples of necessary results which we could be pushing our students to come to understand using their own awareness. I must admit though, there have been times when I've taken this shortcut, but I have found it's more beneficial in the long term to try and persevere. So just to try and illustrate what I mean here, perhaps you can watch this animation unfold and just try and think, what if you're in the shoes of a student, perhaps year 7, year 6, year 7 student, trying to think, what is he doing here? So we can just sort of watch the animation unfold, and I want you just to be thinking, what is going on? What are the numbers in blue? What are the numbers in green? What is it that we're trying to sort of have emerge from this little exercise, which I think is quite a simple looking exercise really. And hopefully you can see by now that the numbers that are being highlighted or circled there in green are of course factors. So what we're looking at is some sort of explanation of factors. Now, this is where I see a small change making a large difference to students, because I haven't written on the board a learning intention that says factors, or I haven't done what I used to do, which would be putting immediately on the board a factor is a whole number that divides exactly into a given number with no remainder, something like that. It's, standard definition of factor. I haven't done any of that. What I want to do is have the students come up with that for themselves. I want them to look at these numbers, the circled numbers, and start to talk to me about why they're circled. And you'll get some students very quickly say, oh, they all go into the end number, they all go into the end number. And through careful conversation and discussion, we can have the students come up with that definition of factor instead. And that's them forming a concept rather than just being delivered some received wisdom. And it doesn't take any longer, really, and it does give students a chance. Instead of sitting back and just watching us work at the board, it brings them on and allows them to try and form these concepts for themselves. Now, I don't have time today to go through the other examples here, but just on this page, just isolate out the prime numbers here. And you could say to them, well, what's special about the row of 3, 5, 7, and see if they can come up with, those are the only ones with 2 factors. And we can say yes, and we call those prime numbers. So I'm just trying to sort of say turning things on its head a little bit here. You could, of course, also do square numbers here. And something that's also nice is to highlight the rows here that have exactly 4 factors. And then that can lead to a really nice investigation into how many numbers have exactly 4 factors between 0 and 100. And that's a really low floor, high ceiling task to do. So I think that it's important to try and consider that balance of arbitrary and necessary. What is it in our courses that we have to tell them, and what is it in our courses that they could maybe figure out for themselves if we gave them the right opportunity? And what we'll try and do is find or create experiences where the students can use their own awareness to come to see what is necessary. Now, many of you, I have no doubt, will have encountered this online publication, which is definitely worth checking out. Great, because shortcuts and tricks are not a good investment in the long term. Things like adding or taking off zeros, it just leads to confusion further down the line. Moving the decimal point with maybe standard form or scientific notation. These are shortcuts and tricks that do not lead to conceptual development. Multiplying decimals, the number of decimal places in the question equals the number of decimal places in the answer. Things like that, although they seem helpful at the time, and for some students it helps them get through the question, it doesn't set them up for any deeper conceptual understanding, and then they either remember this fact or they forget this fact. Things like kiss and smile for adding fractions, the butterfly method. My personal favourite. It's not for us to wonder why, just invert and multiply. Now, apologies about the dog there. She's very excited about MathsConf, just like me. So as I said, shortcuts and tricks, they might seem like a good option for some students, but we are selling them short, and we're only adding to confusion further down the line. So instead, what we want to try and do, and it's harder, is to encourage students to process ideas more deeply. The tricks are superficial, and that's shallow processing at best. Some of Craik and Lockhart's work, which is again worth reading, from the 70s, tells us that with deeper processing and a chance to make meaning, then we can lead students to improved retention and deeper understanding. Manipulatives such as Cuisenaire rods, Numicon, algebra tiles, all of that stuff helps to build understanding, and pictorial representations like bar models and area models really help too. I talked earlier about procedural fluency, but we should also try and consider relational fluency. The most successful students understand multiple representations. You sometimes find that students, maybe higher ability students, don't like to explore multiple representations, and that can often be because they've only ever seen abstract representations, and they feel going back to bar modelling and area models, etc., is too simplistic. So what we need to do is introduce that CA, that concrete pictorial abstract experiences, as early as we can in the maths journey, and it should be consistent, it should be present throughout, which means lots of conversations with primary schools and colleagues across the department. There's no point breaking out the algebra tiles for the first time in year 11 to demonstrate completing the square, because it's more novelty than anything really to do with deep learning. So we're nearly there. School learning is hard. You know, we have to accept that. All learning is hard. It requires effort, and students have a big part to play in that sense. Learning maths can be particularly hard because of its hierarchical nature and the reliance on concepts. And concept formation is different to learning facts. Using tasks that encourage deeper thinking means that although we can't control what students actually think, we can try and influence what they think about. Something I would suggest is that we consider that hierarchical nature of maths when we're planning courses. Really think about the prerequisites, identify them, test them, teach them if necessary. Don't start new work until everybody's ready. Otherwise, we're building on shaky foundations. Think about using research. It's more accessible than ever. There's links throughout this presentation that might take you to something that you might find interesting, and try and really understand how learning works using proven effective teaching methods, and just think about how we can apply that in our classrooms. I don't ever want all teachers to be the same. We can't be. We all have different strengths. Things work better for some of us than others. However, there are some things that are our best bets, and we need to identify those and think about how we can incorporate them into our practice. A big thing for me, of course, is to try and use what we know about cognitive science, consider the limitations of working memory, think about cognitive load, take advantage of proven techniques like the retrieval effect, space practice, and interleaving, like I mentioned before. And what we're trying to do is trying to help those students move from a performance orientation to a mastery orientation. And we do that by letting them know that we value thinking and progress over task completion, and then, of course, just think about that necessary and arbitrary content of our courses, and are we sometimes robbing students of the opportunity to use their own awareness to see those necessary results that are all the way through our mathematics courses. And then, of course, nix the tricks. It seems like it might help at the time because it's the only way they're going to remember it, the only way they're going to learn it. But invest, be patient, time to build the deeper understanding, use manipulatives, use lots of questioning, and you'll start to see the benefits of that in your students. So essentially that is everything from me. We're wrapping up a little earlier so we can perhaps take some questions and then also just give yourself some time to get yourselves ready for the next session. If you've been stuck, like I said, by accident and you've been too polite to leave, and get you joining. I hope that you have taken something from this presentation that perhaps you didn't know before, or even if it's just giving you a little reminder of some ones that you already do, and I've just tried to highlight the importance of them. As I said, my Twitter handle is @MathsConf23, and you can find out all about the things that I've done over the last 15 years or so at my website, MathsConf23.com. It really just leaves me now to slide. If you do fancy some further reading, then these are my favourite little bit pieces that are worth checking out and worth having a read of. So just like to thank Complete Maths and Gary and questions. Gary's willing.
Thanks so much, Stuart, for your presentation. That was really good. There's some questions on the Q&A. If you want to click on the Q&A, you'll see some people have put some things in. I don't know if you want to address them before we finish up.
Looking at not too many. I'll just have a look at some of these just now. So looking at question there about secondary biologically, when we were talking about Geary's work on knowledge, and I believe it is looking at learning from an evolutionary standpoint. So this word biologically that he used in there, I think is connecting up to this idea of the way that we evolve to learn things, and thoughts on that. Lots of great questions here. In fact, hopefully Gary can see these as well, so you're welcome to answer them if you would like. I'm a fan of introducing generalization into lessons, and so of course I think over my career it's only really in the last 4 or 5 years that I've really appreciated that rich connection between number and algebra, and so generalization now is definitely something that I want to try and give pupils and students the opportunity to do, to make conjectures and to try and see for themselves the bigger links. I think it's John Mason that said that a maths lesson without the opportunity to generalize or make conjectures is a maths lesson. So I am a fan, but really just something that's in my way. But a way to think about generalization is always look at that connection between number and algebra. A great question from Natalie. That's lovely, thank you. Any ideas how to help students that come to further a bundle of that they've been taught, and then you've got 1 year to get them through, and that is certainly a challenge indeed, because once students have embraced a trick or a shortcut, I find it very, very difficult to undo that, and so in that case I would quite often say to them that I'm more than happy to use whatever method they're comfortable with, and if that works for them, then at that stage I feel that unlearning what they've learnt is going to be a difficult process. But I would still like to say to them, but please stay with us as we explore this. Just open and think, does this make sense? Does this make sense the way I'm showing you? You don't have to adopt this. You stick to your method that you have, but follow in. There will be times when students actually do say, do you know, that does make sense, and I now know what Kiss and Smile actually is doing, or KFC, something like that. I certainly a long process with a student on a one-to-one basis, trying to get the concept of the multiplicative inverse, and ultimately the light came on, and the student said to me, you know, I've never thought about dividing by a fraction like this, but it makes so much more sense. So I suppose just persevering is the way. Ashton, obviously talking about time there. Do you think there's a time trade-off for students in terms of awareness and using their awareness? Because of course we do feel a time pressure, and it can be so easy to then say, do you know what, today I'm just going to show them how to do this and get on with it because we've got a course to keep up with. And for me, I suppose it's about having the confidence in saying that time invested in allowing students to start to use their awareness, to have that experience of having to think harder, that time invested early on can be bought back later as the students become more prepared to do the thing. And actually, if they do conceptualize ideas, having, you know, taken some ownership of that idea through using their own awareness to get that, then those ideas and concepts are going to stick with them better. And then when you come to rely on them further on in the mathematical journey, they'll be there at hand rather than having to reteach them or drag them back out from memory. So Ashton, your question about time is something that obviously all teachers struggle with. But I do feel very strongly that investing time early on, allowing students to develop those concepts, is time that gets paid back later. Catherine is asking about low stakes quizzing earlier on, and how would you suggest doing this in the classroom effectively? And for me, I have had a lot of success with a fortnightly retrieval practice. 10 or 12 questions which the students mark themselves, which cover some of our recent work, but also some questions that we've done over the past couple of weeks or the past couple of months. And with that routine of retrieval practice every fortnight, then students, they just become accustomed to sitting down and just for 15 minutes working quietly on their own on some questions. I don't mark them, they don't get a grade, and all we want to do is try and encourage students to do better than they did last time. And my experience with this, having done it for a number of years, is that students, when they come to the end of term exams or end of year exams, they then say to me, do you know, that end of year exam was no problem, but it was just like doing another retrieval practice. So low stakes quizzing has many advantages. Retrieval is a big part of it, but it also helps reduce test anxiety and stress. I often say to students, you know, this is really just for me. You're doing this quiz for me, this retrieval practice, I call it that, for me, so that I can understand better what we need to be learning next.
If you can just do a couple more questions, Stuart, and then we'll finish up to move on, or have a break, sorry, to move session 2 yet.
Yep, I'm just having a quick look. There's so many great questions in here. I'm sorry if I haven't actually managed to answer them all. And if you want to tweet them at me, then by all means, and I'll try and answer them on that forum instead. Nikki Clarkson there just asking, how do we support primary colleagues who may not be mathematically confident to nix the tricks? And the thing there is working with colleagues. That's what's so important. Over the last few years, I was head of maths at High School of Glasgow for a few years, and I got to work more and more with the primary school, and there's so much that secondary colleagues can learn from primary colleagues, and vice versa. So in the coming session, which is going to be, you know, the most challenging teaching session ever, given the exceptional circumstances that we've all been living through, it would be great if schools could simplify things and really just focus our energies on what makes a difference and what works. And what makes a difference is teachers getting together and talking about teaching and trying to support one another and trying to come up with a shared idea of what is best practice and how we can really help our students. And Claire O'Brien, I can see she's just got a quick question about the retrievals. Don't mark them or take in. If you don't mark your retrievals or take in marks, how do you use them for intervention? So I get the students to keep a little personal diary of how they did in each question, and it attaches against a sort of granular list of learning outcomes. So they're building a little bit of a profile. I also take these things in and I look at them. I don't mark them, as I say, I don't record anything, but I do look for general areas of weakness that I can then address in my next lessons. Right, I'm afraid I think that is all we have time for. I do hope that you've enjoyed that session. I'm really delighted that you chose to join me for session 1 today, and I hope you have a fantastic MathsConf.